One of the things about chemical reaction rates is that we must do experiments to really find out what the rate law is. We can't just do this from first principles by looking at balanced chemical equations. So I want to describe in this video one of the ways in which we can determine the rate law of a reaction using initial rates. So in this case, that's exactly what our learning goal is, to determine the rate law of a reaction from experimental rates data. This has several features, and so let me go through the method very quickly, and then we'll see it in a couple of examples later on. First, we're going to measure the instantaneous rate of the reaction at the beginning of the reaction. It'd be kind of like determining a race by seeing who got out of the starting block fastest. But since chemicals are utterly predictable after that initial point, that really does tell us something about the long-term behavior. We're going to do multiple trials using different combinations of reactant concentrations. So in other words, we're going to vary those initial concentrations. We have complete control over that, and for each one of those different sets of initial concentrations, we'll measure the initial rate of the reaction. They're going to be compared then between the different trials, and by doing this comparison and by setting up those initial concentrations the right way, it'll turn out that we can determine the order of each reactant, even if there's more than one reactant. We're then going to determine the rate law simply by substituting into one of those equations using the known rate law now for the reaction. So let's see what this looks like in a graph. Now what I want you to do is, let's look at the left-hand side of the graph. This is for a reaction which has two reactants, A and B. And one of the ways that we can control the reactants is by running several trials in which one of the reactants has a constant concentration. It's the same concentration in each of the trials. So now when I run the reaction rate, I'm really looking totally at the dependence of that reaction rate on the other reactant. So on the left-hand side, I've got B as a constant, and I'm showing you the reaction rates for three different initial concentrations of the other reactant, A. And in this case, the thing that's being measured in the experiment is that initial slope, the dashed line that I'm showing in each of those curves. So red, blue, and green represent different experiments, different trials, basically, in which we set up the experiment so that it has a particular concentration of B and, in this case, three different concentrations of A, one for each trial. Now we can do exactly the same thing for B by keeping A constant and running some trials for that and measuring the initial slope or rate for each of those. But that's the essence of the initial rates method. So let's see how this works in practice. I'm going to start with a reaction that has only one reactant, and we'll go through that, and then I'll show you how it works when we have more than one reactant. So let's suppose that we have this reaction of N2O5 breaking up to form NO2 and O2. So there's a lot of things going on in this reaction. The rate law then, while the general rate law might be written as K times A raised to the M power and B raised to the N power, we only have one reactant in this case, so it's going to be K raised to the K times N2O5 raised to the N power. So here's a few experimental data points using different initial concentrations of N2O5, and the initial rate is reported in molarity per second. So how would we go about analyzing this? Well, look at the very bottom row of the table. I've taken that row and I've plugged it into the rate law. The rate law being rate equals K times N2O5 to the N. So when I plug that number in, rate is 4.85 times 10 to the minus 3. The initial concentration is 0.410 molar. So you can see the K and the N are still there because I don't know what those are, but this is what I have for that initial one. Now let's take the second trial and plug it in. So that's going to be in red. So once again, I've simply taken the rate for the second trial, plugged it in for rate, and set the initial concentration to 0.190 and plug that in. Now how do I take these data points and get something useful out of them? Well, the best way is to divide these. Now look what would happen if I divide these two equations. I'm going to get a number when I divide 4.85 times 10 to the minus 3 and 2.26 times 10 to the minus 3. On the other side of the equation, I'm going to divide the k's out. They'll completely disappear, and I'll have 0.41 raised to the n power and 0.19 raised to the n power. What does this look like? So here's the division of the left-hand side. So I'm just dividing those two numbers, and it turns out their ratio is 2.146. Now what about the right-hand side of the equation? So now I'm going to divide the side that has the k's. So we can see that the k's disappear, they cancel each other out, and I end up with a ratio of a number raised to the n power. In this case, that number is 2.158. Now, since these two sides of the equation are equal to each other, this must be equal to 2.146. So I now have an equation that I can solve for n. 2.158 is equal to, raised to the n is equal to 2.146. N is usually an integer, so in this case I'm going to deduce that the integer must be 1. So I've established that this is a first order rate law. Now how do I find the rate constant? Well, what I'm going to do is I'm going to take the third trial here, and I'm just going to plug those numbers in for the third trial. So I've got my rate is 3.26 times 10 to the minus 3 molarity per second. My initial concentration is 0.275 molar. In the rate law, it's raised to the first power. And all I need to know now is what is K. I can just divide both sides by 0.275, and I would find that K is equal to 0.0119 inverse seconds. So this is one example of how one can use the initial rates method to determine a rate law. So it does require a little bit of work. You have to analyze the data, but it's not an impossible amount of work, and it gives you some very useful information. Let's see what happens when we have two reactants. So I've got a lot of information here. Let me sort it out for you. Below the table is the reaction that we're studying. It's two iodides plus a disulfate becoming an iodine ion and two sulfate ions. So there's an iodine molecule and two sulfate ions. So there's a lot going on here. I've got two reactants. I've got the iodide ion and the bisulfate ion, and those are both featured now in the data table at the top. So I've run 3 trials. You can see the initial concentrations for each of the reactants that I've set up in those trials and the initial rate of the reaction. That's the sort of information you would be given. Now, on the left-hand side, I've drawn what the general rate law is going to be. It's going to depend on each of the reactants. Each of them will be raised to some power, which could be different powers, and they will have a rate constant. So how can we analyze all this data to determine a rate law for this reaction? Well, let's look at what we get from the table. Now, what I'm going to do is I'm going to take each of the entries in the table and plug it into that rate law, the general rate law up above there. And that would give me, for trial 1, I would get 1.25 times 10 to the minus 5. That's the rate that's measured, equals the rate constant, times the concentration of the iodide ion, 0.08, raised to the m power, and the concentration of the bisulfate ion raised to the n power. Now I can do the same thing for trial 2. All I'm doing is taking the numbers that are in the table, plugging them into that general rate law. Do the same for trial 3. So this gives me 3 equations that I need to use in order to solve for, in fact, these 3 different numbers, the rate constant, the exponent m, and the exponent n. So how would I use these? Well, one way is I could just take 1 divided by 2. Now, I'm going to claim that this gives me an equation that says 2 is equal to 2 to the m. Where does that come from? Well, I'm taking those first 2 rows, trial 1 and trial 2, and I'm going to divide them by one another. So that the first part is 1.25 times 10 to the minus 5 divided by 6.25 times 10 to the minus 6. When I divide those numbers, I'm going to get 2, exactly 2. And that's where the 2.000 comes on the left-hand side of the far right equation. What about the other stuff? Well, I can see that both of them have the same initial concentration of bisulfate, so that's actually going to cancel out. I don't have to worry about that anymore. What I've got left is this, and that's where I get the factor of 2 to the m. When I divide 0.08 by 0.04, I'm going to get 2, raise that to the m power. I end up with an equation that's 2 is equal to 2 to the m, and I hope you can see the solution of this must be m is equal to 1. All right, what about if I do 1 divided by 3? All right, now in this case, I'm going to get rid of all those marks to clean up the page. And now I'm going to see that these 2 things are at the same concentration, so they're going to cancel when I do that division. I'm also, again, dividing by 1.25 by times 10 to the minus 5 by 6.25 times 10 to the minus 6, so that's going to give me 2.000 again. I'm going to take the ratio of those two numbers, and 0.04 divided by 0.02 is 2. Now it's going to be raised to the n power. So I end up with a net equation that looks like 2 is equal to 2 to the n. Well, it's the same solution that we had before. Now we have n is equal to 1. So now the overall rate for this total reaction is 1 plus 1, or 2. Now when I plug these things into, and I can use any of the 3 trials to do this. I'm going to use the first trial to do this, but I can plug these numbers m and n in to this rate law, and I'll get something that looks like this. So the rate is 1.25 times 10 to the minus 5. I'm just using trial 1 is equal to the rate constant times 0.08 raised to the first power times 0.04 raised to the first power. And that's going to equal to k times 0.0032. So if I just divide both sides by 0.0032, I would find that k is equal to 0.0039 per molar per second. So we've gone rather quickly through this, but I hope you can see that the initial rates method is actually a pretty straightforward method to use once you learn how to set things up and how to put it together.